Good morning. We are moving on now. We've taken care of our two sample proportions, confidence intervals, and hypothesis tests. It's time for means. I'm going to break it down for you. So today we're just going to talk about confidence intervals for means. It's not too much of a stretch from what we learned about confidence intervals for means with one sample, but we have to factor in the fact that there are now two samples. All right. So two sample means. That's what we're doing here. Take some notes. And I'll say CI for confidence intervals. What do we need to do? Well, I want you to remember the equation for the one sample. Okay? The one sample mean confidence interval is x bar plus or minus critical T times S sub x over root n. It's not really all that much different than with one sample, but now we have two. So we have to include the fact that it's the difference between two sample means. Similar to proportions, we're no longer testing for what the population is going to do. We're testing for the difference between two populations. So there's two samples, both of which have to come from some sort of random generation. And we have to look at our conditions for both of those samples. Both have to meet the 10% rule. Both have to meet the normality rule that we talked about, the threefold normality rule. And we're going to see if there's a level of confidence for where their true difference will lie. So here's the equation that takes that into consideration. Here's the two sample confidence interval. It's the difference between the two samples, x bar sub 1 minus x bar sub 2, plus or minus critical T, as before. But the standard error now has two samples to consider. Here's how we find the standard error for the two samples. It's s squared sub 1 over n sub 1 plus s squared sub 2 over n sub 2 under a square root. As we mentioned in previous units, standard deviations don't add, but variances do. So we're going to add the two variances relative to their sample sizes, and then take the square root of that sum. Okay? There's really no special trick to this except for when it comes to the critical T. So how do we find critical T? Remember that the critical T score is the absolute value of the inverse T function, where the area is 1 minus the confidence level over 2, and then we use degrees of freedom. Okay, degrees of freedom was n minus 1, right? What's the issue here? Well, there's two samples, and what if their sample sizes weren't the same? We want to always err on the side of caution. We always call it the conservative estimate. Remember that the smaller the sample size is, the more variable the distribution will be. Well, a larger sample size would mean better data, more consistent data, more accurate, more reliable. But we don't have always two sample sizes that are the same. And I never want to assume I have better data than I truly do. If I have one sample size of 300 and another sample size of 40, that size of 40 is much more variable than the size of 300. And I have to err on the side of caution. We use the smaller of the two sample sizes minus 1. Okay? We call it the conservative estimate because we're being conservative. We're erring on the side of caution. So the conservative estimate is the smaller n minus 1. Okay? Your calculator will not do this. There's an equation. Not a very good, fun, easy-to-use equation. The calculator is going to use it. I'm not even going to write it down because AP scores and practical use will allow for the conservative estimate. But if you want to find the actual formula, who knows, maybe there will be some sort of extra credit at some point if you wanted to use it. On page 600 and, where is it? 640, I think. I know we wrote it down. Oh, well. I believe it's on 640. What we're going to do is just go with that and hope for the best. I'll fix it if I find it later. Okay. It's a crazy formula that is just too complicated to worry about right now. Use the conservative estimate. What's the caution? The calculator will give you an answer that's based on the formula. So it's going to use the degrees of freedom that's based on the equation, not the conservative estimate. It's going to be a little bit different than your answer. For our confidence interval, it's going to be a little narrower than your answer will be. So its lower bound will be a little higher, its upper bound will be a little lower. That does not mean you're wrong. However, don't use the calculator's solution if you're using the conservative estimate. Your answer has to agree with your work. Okay? All right, so let's keep going here with an example, because that's usually the best way these things will work out. Everyone good so far? Well, you can pause it if you're not. Here we go. So here's my example. We take two random samples, one from Connecticut, one from New York, and we find their average SAT math scores. We find that, and I'm just going to say it and build the grid at the same time. So we have Connecticut and we have New York. I know that it's a means prompt because I talked about average SAT math score. I'm going to need the sample size. I'm going to need to know the sample mean and the sample standard deviation. I'm also going to have to verify my conditions. SRS, 10%, and for means, we say is the population normally distributed, or is the sample size at least 30, or is the sample free from strong skew or outliers. All right, so back to my prompt. Connecticut versus New York. All right, I survey and I find that out of 50 Connecticut residents, I find a sample SAT of mean 560 with a standard deviation of 40 points. And my sample of New York took 100 New Yorkers, and their sample mean was 575 with a standard deviation of 60 points. All right, now why did I take more New Yorkers than Connecticut residents? Is it because New York's bigger than Connecticut? No, it's just the sample size. They could have been equal, they could have been lopsided in the other direction. It does not make a difference about the population size, provided we abide by the 10% rule, which we're going to verify next. But it just is the sample size we're given. Was it an SRS? Well, I did say it was an SRS, or I at least said it was randomly drawn. 10% rule. Do you think that Connecticut residents number more than 500? Obviously. Do New York residents number more than 1,000? Obviously. Was the population given as normally distributed? I don't recall saying those words. So, no. Is the sample size at least 30? Well, 50 and 100 definitely qualify as at least 30. Now, so far as the skew or outliers go, I don't care. I've already verified, so I don't care. Doesn't matter. We don't have to go that far. Okay, moving on to our actual equation now. Well, before actually, I gotta find one more thing. What do I have to find? The critical t-score. What is critical t? Now, again, you can use your calculator directly, but what is critical t going to be? It's the absolute value of inverse t, parentheses 1 minus, I think I said 95%, but if I didn't, let's say it now. We're trying to build the 95% confidence interval for the difference between the populations of Connecticut and New York in terms of SAT math scores. Okay. Well, 1 minus 0.95 over 2, and how many degrees of freedom will I use? My sample size was 50 versus 100. What should I do? That's right, use the 50. So 49 degrees of freedom. While we're here, and I remember, the graphing calculator is going to use a degree of freedom that is almost always going to be a little bit less than the sum of the two sample sizes. If you verify with the graphing calculator, what you're going to find is it'll say degrees of freedom are like 147 or something like that. We'll look at it later. Doesn't matter. We're going to use the conservative estimate. What do you get here? Well, I got 2.0096. Go to 4 decimals, please. My formula, x bar sub 1, that's 560, minus x bar sub 2, 575, plus or minus my critical t-score, which I know is 2.0096, times the square root of 40 squared over 50, plus 60 squared over 100. I know it seems obvious, but please make sure you put the numbers in the right spots. It happens more often than I'd like to say that people get the values in the wrong spots. What helps keep it straight? This grid. Use it. Organize your data. It makes it so much easier. No, it doesn't count for points, but it helps you get the right answer. So I guess in a sense, it does count for points. Now, right here we have 560 minus 575, that's negative 15. Plus or minus 2.0096. The standard error, if you calculate it in the calculator, is 8.2462. Well, that means that it's negative 15 plus or minus 16.5716. That gives me a confidence interval that is negative 31.5716 to positive 1.5716. Okay, well, it's kind of lopsided, but what's inside the interval? The number 0. We want to say that we are, and again, I'm going to ellipse this a bit, but we are 95% confident that the true difference between the population's average SAT score between Connecticut and New York is between negative 31.5716 points to positive 1.5716 points, which means that it starts off in New York's favor, but at 95%, it actually does extend into Connecticut's favor. So there is a 0 contained on the interval. I don't care that it's very close to the upper bound. The question asked to just create the interval. So we did. If it asked us, do we think that the data would be significant at the 5% alpha? Well, 5% alpha corresponds to a 95% confidence interval. 0 is contained within that interval. We'd say, doesn't look like it's significant. Now, the step back and look at it. It looks close. So what might happen if we change our level of confidence? I want you, for homework, just to take this exact same prompt and run it for a 90% confidence level. All right? 90%. All you're really changing is the critical t-score. But I want you to find the interval that it would create and give me some interpretation based on that. Okay? The quick double check, again, you can use the 2 sample t interval function on the calculator stat tests. It's going to use a degree of freedom that is a little different than what you're using. You're using the conservative estimate. It's going to use the equation. It was page 640. So look at it if you want to. You do not have to. It's going to be similar but a little different, a little narrower. Take a look at it. But I want you to run the 90% interval for homework, and that's it. Have a great day.